Okay, this is Neil Patwari. I'm going to talk in this segment about coherent M-ary FSK and how to come up with the probability of bit and symbol error expression from the union bound. So with coherent M-ary FSK, we don't have an exact expression that comes out to be a neat little formula. Instead, I'm going to show you how to use the union bound to come up with an expression for the probability of error. And so I've taken the liberty of copying the constellation diagrams for FSK for m equals 2, m equals 3. And if you forgive my use of this red line as a fourth dimension, then I'm drawing for FSK, just to give you an idea of some of the intuition behind the math. So the union bound again says that we use this formula. We look at the neighbors of I. The neighbors of each symbol. And so let's think about that. In our 2FSK, we have each symbol has one neighbor. In m equals 3 FSK, each symbol has two neighbors. And in m equals 4 FSK, each symbol has four neighbors. So we're talking about m minus 1 neighbors. So this sum is going to be over m minus 1 neighbors. And the next thing is, what is the distance to those neighbors? You can see it here in m equals 3 FSK. These distances are identical. They're both a away from the origin. So to calculate this distance, we can use the Pythagorean theorem to come up with the fact that this distance, d, is equal to square root of 2 times a, if, this is a away from the origin. All these distances are going to be the same, so all these cube function terms are going to be the same. So when we write this expression again, we're going to have 1 over m. We're going to have the same exact cube function. So we're going to multiply by capital M different symbols, and we're going to multiply by the neighbors of each symbol, which is, like we just said, m minus 1 neighbors, and the cube function with the distance being the square root of 2, that quantity squared. So I'm going to have 2a squared divided by 2n naught. And it's our standard practice to write the cube function in terms of the energy per bit. The energy per symbol, let's start out with the energy per symbol, is 1 over m times the energy of each one added together. But this is just a sum again of m times the a squared, because every symbol is exactly a away from the origin, so its energy is a squared. So we get a squared for the average energy per symbol, and the average energy per bit then is a squared divided by log base 2 of m. So what we do is we plug in for a squared. This means that a squared is equal to energy per bit times log base 2 of m. And so we can rewrite this expression, canceling the m's. We've got m minus 1 times the cube function of the 2's cancel, and the a squared becomes energy per bit times log base 2 of m. I'm going to write this log base 2 of m out front, and then the EB over n naught. So the question is, what is the probability of bit error? Is related to the probability of symbol error by this factor of m divided by 2 divided by m minus 1. And this is the same reason that we talked about in the previous segment on non-coherent M-ary FSK. And this probability of symbol error is the same, I guess. So far I should actually write an equal sign here, but we're going to end up using the less than equal to sign because we've used the union bound to come up with the probability of symbol error. The m minus 1s are going to cancel, and I'm going to be left with m over 2 times the q function of the same argument, log base 2 of m EB over n naught. And I guess I should specify that the log base 2 of m is a constant factor and the EB over n naught is not part of the argument of the log function. So I'll put in parentheses there, and that's it.